At this stage, we know how to deal with derivatives of complex functions. So let's now take the next step and also try to look at integrals. Now, if we go back to real valued integrals, that was very easy. We had an integral of a function f of x dx between the bounds a and b. So these were just 2 points on the real valued number axis. Now what we would like to write down is something like an integral of a complex function f of z dz from a starting point z0 to an endpoint z1. Difference in this case is that we don't have points on a real valued axis. We do actually have points in a complex plane, which is two-dimensional. So this means we have an integral from this point to that point. And moreover, we have different ways we can travel to go from the beginning point to the end point. So in essence, this also depends on the path we take on the curve that links z0 to z1. So we should actually write something like this. So this becomes an integral over a curve. Now, this reminds us a lot of a different situation that we have also in real valued analysis, but then vector analysis, the line integral of a scalar field, right? So in this particular case, we had a similar situation where we had an integral over a certain curve of a scalar field, f of r. So a scalar field is basically a black box which as input has a vector. In our case, it'll be a vector in the 2D plane. And as output just spits out a real valued number. And then you had the integral, line integral here, where we multiplied with ds, which was the length element, the line element here. Now this was defined in the following way by making use of a trick called parametrization of the curve. We basically have a mapping from a certain parameter t to a point r of t, which then traces out the curve in such a way that, for example, if you plug in a here, you will have the begin point, and if we plug in b, we have the end points of the curve. So this curve was parameterized by t, and that reduced it to a simple one-dimensional integral over t from a to b. So a again is the parameter that gives rise to the starting point, and b is the parameter that gives rise to the endpoint. And then f of r just becomes f of r of t, because t parameterizes r along the curve. And then this length element, this line element ds, that turned out to be equal to having a vector r of t, which we take the derivative with respect to t. And then that vector, we take the norm. And if we integrate that, if we multiply that by dt, we basically have a real valued number here. And if we integrate this, we expect a single real valued scalar, which is what this definition basically tells us. Okay, so our case in the complex plane looks very similar, but not identical. But at least we can look at this for inspiration and see how we can tackle the integral of a complex function, f of z dz, along a certain curve C. So again, we're going to use parametrization in a way that we have a mapping of t to z of t. And if we plug in a as t, then we get z of a is going to give us our starting point, and z of b is going to give us our endpoint z1. So in a very similar way, we're going to write that as the integral from a to b of, f of vector r of t now just becomes f of complex z of t, okay? And then for the second part here, let's use some inspiration, but not exactly copy that. And we're just going to write that as z prime of t dt. So going from here to here, we just replace f by z, and we get rid of these norms here. So why do we do that? Well, in this particular case, we wanted to end up with a single scalar real valued number, right? So this gives us a real valued number. But if you look at this derivative of this vector, that's just a vector. So in order to get a real valued number, we need to take the norm such that we have, for the end result, also a single real valued number. In our case, we strictly speaking don't really need that because we're fine with ending up with a single complex number for our answer. This vector is also a complex number intrinsically, and this thing is also a complex number. So in this particular case, we really don't need explicitly to add the norm. We could do that, but we just choose not to do it, and we have this much simpler looking end result. By the way, it's worth pointing out again that z prime t dt, well, that's of course a shortcut for dz dt dt times dt. And what this thing basically is, it's the chain rule applied to z of t, right? So in essence, what we've done is we wanted to calculate this thing. We've just parameterized this in such a way that we replace z by z of t. So this becomes f of z of t, and this then becomes d of z of t, and then the chain rule gives us this thing here. So a very logical definition, makes a lot of sense. So this is what we're going to use as our definition for an integral of a complex function along a certain curve C. Okay, good. So now that we have that definition, let's apply that to a very simple but important example. So the example we're going to look at is an integral over a certain circle centered at the origin. So the circle has radius r. This is our curve. And we're going to look at the integral of z to the power of n dz over our curve. This particular curve is a closed curve. It's a contour, basically. And if we're dealing with closed curves, with contours, then by definition, we're going to also signify that in our notation by adding a little extra circle here, which is just for flavor, just for fun. So this extra circle means C is closed. Okay, but that's just notation. So what I suggest you do now is pause the video and try and come up with a suitable parameterization of our circle in polar coordinates. And if you do that, see if you can apply the definition and then calculate that particular integral for different values of the coefficient of the exponent n. So pause the video and go ahead. So the parameterization is going to be as follows. So if we look at a point C here on this circle, we can write z as r exponential j theta, with then theta running around from 0 to 2 pi. So theta here plays the role of our parameter t. So if theta increases from 0 to 2 pi, we just trace out our circle here. So this is the parameterization that we're going to use. And then we just simply apply the definition. So the integral z to the power of n dz becomes an integral over theta from 0 to 2 pi. Z to the power of n becomes r to the power of n exponential j and theta. Okay. And then for our second factor here, so this is going to be z prime of t dt. So we're going to take the derivative of z with respect to theta times d theta. So that simply becomes then j r exponential j theta d theta. And now we're back in very familiar territory. This is a simple one-dimensional integral of mostly real stuff here, apart from some prefactors. So speaking of prefactors, the j can move out. Also the r can move out because we integrate over theta, which means that r is a constant here. It's a circle. So this becomes then r to the power of n plus 1, the integral from 0 to 2 pi of exponential j n plus 1 theta d theta. Okay. If you didn't find this on your own, now could be a good time to pause again and work out the end result. It's important here that we make a distinction between two cases, depending on whether or not this n plus 1 here is equal to 0. So let's first start by saying that n is different from minus 1. And then our integral becomes j r to the power of n plus 1. And then this is a very trivial integral, basically. This is going to give us exponential j n plus 1 theta divided by j n plus 1. And evaluating that between the bounds 0 and 2 pi. Now, this complex exponential has period 2 pi. So if we integrate between 0 and 2 pi, we just get 0 at the end result. So in case n is different from -1, the end result is 0. In case n is equal to -1, we can't use this basically, because then we would be dividing by 0, which is strictly forbidden by the mathematical gods. So let's not do that, but let's explicitly write down what would happen if n is equal to -1. If n is equal to -1, we basically have the integral of dz over z and being equal to -1. And then if we look back at that expression over here and see what happens if n is equal to -1, that becomes j r to the power -1 plus 1, so that's just 1. And then we have the integral from 0 to 2 pi of exponential to the power 0, basically d theta. So it's an integral j from 0 to pi d theta, which is just 2 pi j. So in this case, we have a different result. So it's not 0, but it's 2 pi j. Two final remarks here. First of all, note that there's nowhere an r in our end result. So the radius of the circle doesn't play a role. And then another thing I would like to say is that this may look like a very simple, trivial exercise to show you how to work with integrals of complex functions. And in a way it is, but it's also a very important exercise, a very important result, because the fact here that integrals of polynomials are non-zero only when we have an exponent of -1 here is a very important end result, which will come back to haunt us or to help us, whatever, in later stages of this chapter. So very important result here.